Bon ben, je pense qu'on va commencer la dernière session des journées BDA. Je tiens d'abord à remercier au nom des orateurs les présents ici. Et puis, je te donne la parole, Konstantin, pour faire ton exposé. Merci.
Okay, thank you for the introduction and welcome to my talk. It seems that I will have the difficult task of keeping the few of you who are still remaining here awake after lunch. I will try to do my best. So, for those of you who were at the OD Base conference this September, probably they will experience a kind of a déjà vu because I have already presented this work there. So this is a work which focuses on a particular problem in the ontology matching field. And particularly, we focus on the resolution of one certain kind of terminological heterogeneity across two different ontologies. And this work has been mainly done by our PhD student, Owen Go, together with myself and Zohra Bellahsene. So, I suppose that most of us are aware of the ontology matching problem. We have seen that ontologies have been widely applied in various fields, particularly notably in the semantic web applications. The problem is that many ontologies are being created in a decentralized manner, and the human interaction is very important, which leads to the creation of different ontologies, which tend to describe the same domain of interest or overlapping domains of interest. This has led to the problem of ontology, what we call ontology heterogeneity, and it can be manifested on many different levels. For example, on a syntactic level, concerning the particular formal language in which an ontology is expressed. On a terminological level, regarding the actual choice of vocabulary on naming convention, on conceptual or structural level, etc. And the aim of an ontology matching system is to detect in an automatic manner the correspondences between the elements of two different input ontologies. So, for example, in this toy example that you see here, the matching tool would be able to detect that employee from the blue ontology corresponds to staff from the red ontology. So this is how a generic framework for ontology matching and evaluation could look like. So what you see in the lower left corner here would be the ontology matching tool, which is composed by different sub-systems, which focus each on different heterogeneity type. We can have a terminological matcher, which we can have a structure-based matcher, a semantic matcher, and a mapping selection module, which serves as a kind of filter on to filter out candidate mapping pairs of concepts. Then we feed two ontologies onto this matching system. They are transformed in a certain way, and an alignment is discovered between these two ontologies. And in order to evaluate the quality of this alignment, we need a reference matching, which is already available, either produced by experts or from other sources. We compare our discovered alignment to this reference alignment, and we measure the quality of the alignment by using standard evaluation techniques from information retrieval, such as statistical measures like precision recall and F-measure. So what I'm going to talk about precisely in this talk, what I'm going to focus on is the terminological heterogeneity between ontologies. So we are interested in measures for similarity between concepts based on the terminology. So our hypothesis is that a concept is identified by the meaning of its labels, like meaning that can be found in dictionaries. And therefore the heterogeneity between concepts will be defined as any difference in the spelling of their labels. So any difference in the naming convention that has been chosen to refer to one and the same concept. So assuming that the concept is language independent. Okay. we have introduced here a scale of the different heterogeneity types, starting from type 1 heterogeneity, in which we find almost identical labels. There we talk about tiny variations in spelling, like typos or singular versus plural tense, and so on. Then we can have more complicated cases in which we have composed labels, and we have token-wise similarity of the components of each label. For example, you can have a conference banquet versus banquet conference. Then we can have a little bit more manifested heterogeneity when we have partial token-wise similarity. So this is the case when one of the labels is, say, conference banquet, and the other one is dinner. So we refer to the same event, so the same object in the real world, but we have two quite different ways of referring to this object. Then we can have acronyms and abbreviations and synonyms when we have totally different labels chosen for the two concepts, to label the same concept. Of course, there are many measures that exist out there already which are able to deal with this kind of terminological heterogeneity. In fact, so many different measures that one might ask legitimately the question, why do we need to introduce yet another measure? We have seen that there exist measures which are based on a string, manipulating the strings that denote the concepts, like edit-based similarities, such as Levenshtein and the ISAP measure, which has been successfully applied in the ontology matching field recently. Then we have the token-based group of measures, which first split the labels into the composing tokens, and then apply a measure from the edit-based group in order to infer the similarity between the tokens that compose each label. On the language-based side, we have also a set of a bunch of measures which have been applied recently and through the past years. We have internal measures which look into the linguistic properties of terms. So this means to compare and remove all kinds of information relative to, for example, flexion, to tense, to conjugation, in order to strip the words down to their morphological roots, and then go back to the group of string-based measures. We can also use some more advanced techniques. For example, go and have a look into dictionaries in order to find the meaning of the different terms, or to semantic nets, where we could infer the semantic distance between different terms. And then, of course, we can have also hybrid measures, which combine language-based techniques together with string-based techniques. So each of these techniques have their shortcomings, and I will shortly go through these shortcomings in order to motivate the measure that we have proposed. The string-based measures, in the token-based subgroup, they can handle compound labels, but they're less sensitive to word swaps. So in the example of conference dinner and dinner conference, a token-based measure would be able to detect this similarity. But sometimes they need external resources, so large corpora, in order to assign weights to the tokens that are included in each label. Then we would have the edit-based, which are usually used like an internal measure inside each of the token-based measures. And they're good at handling heterogeneities of type 1, so really tiny variations in spelling between the different labels. On the side of the language-based techniques, we have two common problems which appear both for internal and for external measures. First one is that these measures are able to deal with single words and not with compound labels. So here I have given one example. The label PhD thesis cannot be found in WordNet or in a semantic network, although each of the composing parts, PhD and thesis, can be found. So we need some additional technique in order to go and look for the composing terms. And then some typos that might appear in the labels can prevent us from from matching these terms onto their references in the vocabularies or in dictionaries. As for the combined measures or the hybrid measures and techniques, one problem here is that they often fail when the number of shared tokens between the two labels is small. So we really need to have a certain number of terms that the two labels have in common in order to apply one of these measures. They also require often some external resources in order to compute weights on the terms, which are not always available in the ontology matching domain. And some of these measures are asymmetric, and asymmetry is not a very nice thing, so it would be nice to be able to overcome this problem. So here's again our scale with the different techniques. We have seen that the edit-based distance would be good to deal with type 1 heterogeneity. We have the hybrid and string-based measures that can deal with the type 2 of heterogeneity. And synonyms can be handled by language-based measures, usually, and some hybrid measures. However, the partial token-wise similarity, I recall the example, if we have a conference dinner versus banquet. This is a kind of similarity which cannot be handled up to date with any of these existing measures, at least not with a satisfactory precision. And this is a type of heterogeneity on which we are focusing in this work. And we have proposed an extension of the well-known Tversky similarity measure. I will go into more details in a while, with the objective to be able to handle compound labels in the first place, to make use of the textual information which is only available in each ontology. So we don't go to look into any external resources, into dictionaries or to large corpora in order to calculate weights. The weights, indeed, to our tokens are computed only on the basis of their relative importance within each of the ontologies. And we will see how in a while. And as I said, we want that the ontology is the only and entire resource that we need in order to compute the weights and to compute the similarity between the labels. So, first, there are two things about this approach. First is the computation of weight. How do we assign weights to each of the composing tokens in our labels? And the second thing is how do we use these weights in order to compute similarity? As for the weight assignment, we go into the field of information theory and we take a already made measure of weight, which is the information content. We know from information theory that the information content, or the entropy, is inversely proportional to the probability of occurrence of a given term. So we take this quantity as a measure of the importance of a term within the ontology. And we compute for each given word or token its weight in the following manner. So this is something which is rather standard and has been already done in many different fields. And then here we come to this wonderful slide on which I'm presenting the similarity measure that we have developed based on the well-known Tversky similarity. So Tversky's measure is based on a very simple idea. We have two objects and want to compare their similarity. Each object is modeled as a set of features. And if two objects share at least one feature, we can infer that these two objects are similar at least with some aspect, into some aspect. So this measure can be expressed in different ways, depending on the setting of different internal parameters which are given into this measure. And one of the ways of presenting this measure is what you see here. This is also known as the dice coefficient. So what we need to estimate is what do we have in common between two objects, and what we have which is unique and describes only one of these objects, and on the other hand only one of the other objects. In our case, the objects are labels that denote some concepts. Let's say that these are the labels S1 and S2. We have some kind of a tokenization function and a similarity function, a similarity measure of some kind. For example, a string-based similarity measure or some more simple, more basic similarity measure, which is used inside of the similarity computation. And what we try is to come up with a evaluation of this quantity of intersection, or what do two labels of two concepts have in common. So we define a custom function of intersection, which is not symmetric. We define first the number of shared the set of shared tokens between two labels. First, for what is common between S1 and S2, and then, in the same way, what is common between S2 and S1. So what you can see here is that what we're doing is, for each of these quantities, which are summing the weights of each of the tokens, scaled by the tie of this token to the tokens of the other label. So these ties are represented by the similarity, the maximal similarity between the tokens. And what describes each of the labels individually is simply the sum of their weights. Okay, so here I have an example which hopefully would be clearer. So we have the label S1 and S2, conference participant and attendee. And we have the token similarity between conference and attendee, which is given as 0.1, and the similarity between participant and attendee given as 0.9. We have the common part between S1 and S2, which is defined by the set which contains only the token participant. And then we have the common part between, this time, S2 and S1, which is the set containing the element attendee. We fix a threshold of 0.75 for the similarity. And the extended Tversky similarity here, denoted by ET, will be given in the following way. So you see that there is a weight computation which is involved in this similarity measure, and the weight that we use can be any existing weighting function from the literature. We have done experiments by using both the well-known TF-IDF weighting, well-known from the information retrieval field above all, and also our information content-based weighting that I have just presented. And I will go briefly through several results that we have obtained by testing our approach on two different data sets which are well known in the ontology matching field. One of them is the conference data set from the Ontology Alignment Evaluation Initiative, and the other one is the I3CON data set from the corresponding I3CON conference. And these are the results that we have obtained. I'm sorry that one of the graphs is a little bit cut from the side. So how we are supposed to read these results? On the x-axis, we have a threshold which corresponds to the mapping selection threshold in our matching task. What does it mean? This means that we set a value for the similarity function, above which we will consider a pair of concepts as potential match. And for each value of this threshold, we compute the F measure for each of these listed below measures of similarity. So we have used our measure of similarity and compared it to several other representative measures of terminological similarity. And here we have compared our method to weightless methods. So the other measures that you see here do not use weights in the similarity computation, whereas ours does. And the two graphs represent, the diagram on the left represents the results when we have used as an internal weighting function the IC-based measure, so the information content-based measure that we have introduced. And on the right, you see the same result, but this time using the TF-IDF weighting function. So as you can see in blue, so the curve on top is corresponds to the F measure which have been computed for each of the thresholds of our method. And we can see that for any given threshold of the mapping selection scale, the F measure is, that we obtain is higher than what the other similarity measures obtain. And we have a similar situation. Note that here the coloring code changes. We have our measure in red. I'm sorry for that. So here again we have done the same thing on the same data set, but this time by comparing to other measures that also include weight computation in their definitions. And again on the left you have the IC-based weighting, and on the right you have the TF-IDF weighting. Now the I3CON dataset, the situation is a little bit different. We can see that our method is still among the best performing, or to be precise, among the 2 best performing methods, but is slightly dominated for certain threshold values by the ISUP method, which is a token-based similarity measure. And again, here we compare to weightless measures, and on the next slide we compare to weighted measures, and we have a similar situation. So the reason for the fact that we obtain a slightly worse result on this data set as compared to the conference data set is basically certain properties of this data, in particular the fact that the ontologies that we consider in this data set do not contain the type of heterogeneity that this particular measure is able to deal with. But this is important to see this comparison as well, at least to be reassured that our measure does not globally perform worse than the other common similarity measures. So I have come to the conclusion. The ontology matching task, for those of you who are familiar or at least have a slight view on this problem, is a complex process, and usually it comprises the integration of several different modules which interact in complex manner between each other. And of course, the quite straightforward intuition would be that if we achieve an improvement on one of these modules, we will also observe a global improvement of the performance of an ontology matching tool. And this has been the motivation of this work, to boost the performance of a terminological matcher within a global ontology matching system. So we have proposed an extension of the well-known Tversky similarity measure, together with a particular weighting function inspired from information theory, which can handle compound labels. And we only make use, as I already said, of the textual information which is contained within each ontology. So these are the concepts, names, and eventually some descriptions of the concepts within the ontologies. And the weights of the tokens are assigned with respect to the token's relevant importance within each ontology. And I thank you for listening.
Any questions?
Yes.
For the experimentation, you have 2 different ontology and measure the similarity. For the experimentation,
Yes.
You take a different ontology, and I do not really understand. You take different and measure.
So this is a standard. I can go back to this figure, a standard setting. You have 2 ontologies, what I have called here source ontology and target ontology. And these are the ontologies that you want to align.
Yeah.
You produce an alignment, and then you compare it to a reference alignment which already exists. So this is in the benchmark. Okay?
Okay.
And then, of course, on the basis of this comparison, we can go and compute precision recall and F measure.
And how size the ontology that you take for the experimentation?
Sorry, how?
The size,
The
number
size.
of concepts.
Okay. Well, it's about between 60 and 120 concepts, each of the ontologies. So in the conference data set, we have around 12, 13 ontologies that we have compared, so pairs of ontologies. And in the I3CON data set, we have around 7 or 8, if I'm not wrong, ontologies that we have compared. So these are really medium, small size ontologies.
And okay, you use your metric, your similarity measure for ontology, for vocabulary alignment. But there are also people that are using same things for entity matching. But entity matching is more challenging because you have a lot of entities. Do you think it's the computation of your similarity is fast enough to handle online entity matching?
Yes, this is a good question, and indeed, I personally do not really I don't have a background in the database community. So this is one of the reasons why I would like to present. I wanted to present this paper here because what we have done is to apply this measure in the ontology matching field. Of course, there are some analogies and similarities to the entity matching or record linkage fields. Fortunately, I'm not able to give any details on that. I would assume that scale would be very important, and in our case, of course, scale is, we were in the size of, as I said, 60 or something comparison of different labels. Then there is another thing, which is that here we only go and look into the terminological similarity. Mm-hmm. Usually a ontology matching tool would take also into account the structure of each of the respective ontologies. Different also semantic consideration would be taken into account in order to feed all these into a common matching algorithm. We have only produced a similarity matrix for two sets of labels.
I can be more precise. There are people that are doing entity matching on the fly. Mm-hmm. So you cannot, you don't have time to compute complex similarity measure, analyzing the structure of entities. Yeah. Sometimes you have to do it very fast, mm-hmm. just by comparing strings. I didn't see how complex it is to compute your similarity metric. Is it fast?
I cannot give you any details on that, unfortunately. As I said, we were not really concerned with this kind of issues when we introduced this measure. It might be that OA, the person who has implemented the algorithm, could give you more details.
Maybe I can answer, because it's a common discussion. So if you have, the question is, if you do entity matching, what is it important for you? Because if you want really good quality, then maybe you don't mind the time. You want to invest in time. And if you want to do a large scale, you need to accept that it's against the quality. So it's a balance between the two. And well, I cannot answer this. What is the complexity of this method? But this is a common trade-off you need to do.
Other questions? I have just one. You compared your method with the others with respect to the quality of the results. What about the execution time? Is it faster? Oh.
It goes once again into the same discussion. This measure is supposed to be part of a global ontology matching system. Here what we have tried is just to see how far we can go in terms of F measure, so basically precision if we allow the threshold to become greater. So yet again, the execution time has not been a consideration in this work.
Okay. So let's thank the speaker again.